We know that electromagnetic waves can have some specific polarizations, so let's see how these polarizations appear in quantum field theory. We start with a massive case for a classical field obeying Klein-Gordon equation and under the Lorentz condition. We know that for spin 1 field, we have 3 degrees of freedom, so we can expect 3 polarization for the field, and therefore we can write the expression for the field using a sum over 3 components of the polarization vectors. So up to a normalization, these are the polarization vectors. We have 3 of them for j equal 1, 2, and 3, and there are 4 vectors. They are explicitly function of the 4 momentum p, and in fact, because of the Klein-Gordon equation, we see that if we substitute this expression into Klein-Gordon equation, the only possibility is for the field to be on mass shell, so for p squared to be equal to m squared, and therefore epsilon, the polarization vectors are 0 unless p is on mass shell. We also have to obey Lorentz condition, which implies that, and we also choose a convention for the normalization of the polarization vectors. Note that this is a normalization which holds for each vector epsilon j, so we are not summing over j here. To get an explicit expression for these polarization vectors, we need to choose a basis. So we choose a canonical basis by convention, where the momentum is aligned along the z-axis. And because we only consider momenta which are on mass shell, we have the usual relationship between energy and momentum. We can now define 2 transverse polarizations which are perpendicular to the linear momentum and 1 longitudinal polarization which is parallel to the linear momentum. You can verify that these obey both Lorentz condition and the normalization condition. So let's now move to the massless case. We already see that there is a problem with the longitudinal polarization because we divide by m. So that will not be well defined in the massless case. But that's not really the main issue, because what we will see is that in the massless case, this longitudinal polarization becomes unphysical anyway. So how do we see that? First, we need to realize that the main difference between the massive and the massless case is that in the massless case, our Lagrangian is invariant under the following gauge transformation. Indeed, you can verify that f mu nu is invariant under this transformation. However, if the field was massive, we will have a mass term in the Lagrangian, and this mass term will not be invariant under the gauge transformation we just defined. So the invariance under this gauge transformation is only true in the case of a massless field. So this gauge invariance allows us to remove another degree of freedom by choosing the function alpha, because that's an arbitrary choice, and that's called gauge fixing. So if we fix a gauge, we remove 1 degree of freedom, and therefore we end up with only 2 degrees of freedom for the massless case. That means we will end up with only 2 physical polarization vectors, 1 for j equal 1 and 1 for j equal 2. So we now want to determine what are these physical polarization vectors. The first thing we will do is to absorb the sum into epsilon in order to simplify the notation. As in the vector case, we use the fact that our classical field obeys Klein-Gordon equation, here with m equals 0, as well as the Lorentz condition. So the Klein-Gordon equation tells us that the polarization vectors are non-zero only when the momentum vectors obey p squared equals 0, which makes sense because that's when they're on mass shell when m is equal to 0. And the Lorentz condition tells us that the 4-vector polarization vector is perpendicular to the 4 momentum vector. But so far, we only used the Lorentz condition to reduce from 4 degrees of freedom to 3 degrees of freedom, as in the massive case. And we now need to make use of our additional degree of freedom, which we can reduce thanks to gauge invariance. And for that, we need to fix the function alpha of x. And for example, we are going to choose del squared alpha equals 0. We can verify that the field we obtain after the gauge transformation still satisfies the Lorentz condition. Indeed, this term is 0 because of Lorentz condition, and this term is 0 because of our choice of gauge. So we see that we need to find alpha which obeys this equation, which looks like a Klein-Gordon equation with m equals 0, and we know the kind of solution we then expect. That will be a sum of plane waves with a condition on the 4 momentum so that they are mass shell and k squared equals 0. We can then use this explicit expression in order to express the gauge transformation of the field. So we see that residual gauge freedom is equivalent to allowing the polarization vector epsilon mu to change by a factor of k mu. And we can use this freedom, that is choosing beta, in such a way that we can simplify our polarization vector. So we can, for instance, arrange for the time-like component of epsilon to be 0. So we just need to choose beta so that we shift epsilon, the time-like component, to be 0. And once we got rid of the time-like component of the polarization vector, we see that we can rewrite the Lorentz condition. And we see that this naturally kills the possibility for longitudinal polarization, and therefore only the transversal polarization survives. The two we had before, which are linear polarization, we could also have circular polarization, left and right, as follows.